this is the second class of Green's theorem and its application. Okay, and in this class we discuss about an important, very important application of Green's theorem, and this is so that half into circulation over C x dy minus y dx represent the area bounded by the closed curve C. Okay, this is very important application of Green's theorem, and this is an independent problem of Green's theorem. And using this problem, we can solve so many problems of this type. If we have to find out the area of the ellipse by Green's theorem, then we use this result. Also, to find out the area of the asteroid, also use this result, and or find the area of the circle by using this result, and all are using Green's theorem. Okay, now see that what is the problem and what is its solution. Here, if we compare Green's theorem, the left hand side of Green's theorem with it, then we comparing, we can write m, this is equal to x by 2, this is m equal to minus y by 2, because half into minus y into dx here. So the coefficient of dx is m, and n, this is equal to half into x. Okay, so we have to find del m by del y and del n by del x, and we get del m by del x, this is equal to half, and del m by del y, this is equal to minus half. And using Green's theorem, we get half into circulation over C, this is x dy minus y dx, and this is given by double integration over r. Del n by del x means half minus half into dx dy. Okay, and this is the closed curve C in anticlockwise direction, and this is the area R. This is R. Okay, and this gives half plus half means 1, double integration over R dx dy. So this is nothing but the area of the region R bounded by the closed curve C, and this is our the first result. Okay, now using this result we find an area of this curve, either this curve, either this curve. We try the first one, and this is ellipse. We find or we write all the equation in parametric form first. That is x equal to, we know that x equal to a cos theta and y equal to y equal to d sin theta. Okay, now dx means a sin theta d theta, a sin theta d theta, and this is minus a sin theta d theta, and dy, this is b cos theta d theta. Now we apply dx dy x y in this result. Okay, and we get area R, this equal to half into circulation over C, because R equal to this. What is x? X is a cos theta. And what is dy? dy means b cos theta. Okay, minus this is y, so y is b sin theta into, and this is dx means minus a sin theta, so this is plus a sin theta into d theta also. Okay, here a d theta and d theta, we take d theta common from both sides, and this is ab by 2 into circulation over C, this is cos square theta plus sin square theta d theta. So this is ab by 2 into circulation over C d theta. Now we draw a rough sketch of ellipse. Okay, and any point on the ellipse P, this is a cos theta comma B sin theta. This is the parametric form and this is the theta. Okay, so theta varies from 0 to 2 pi and the range of the integration is AB by 2 into integration 0 to 2 pi d theta. So clearly this integration is AB by 2 into 2 pi, so pi AB. Pi AB is the result of the first problem. This is pi AB. Okay, and similarly we prove all the result by using this theorem of this problem very easily, like this problem. Okay, thank you for watching.